Rocket
Danielle Beatty.
Jake Gilmore.
Teak Larwood.
Matt Tickner.
We initially predicted that the rocket would launch the highest when the canister was filled halfway with hot, near boiling water, and 1/4 of a fully crushed Alka-seltzer tablet was used. These predictions were made with the thought that the increase in surface area when using the crushed tablet would create more nucleation sites, leading to a faster reaction and a higher launch. The amount of tablet used with this combination of water is based on the prediction that 1/4 of a tablet will be consumed completely, and that any larger of a tablet would just add unnecessary, unused material. The following video shows 3 separate water and tablet size combinations, the third being the highest and best launch recorded.
And I think it's gonna be a long, long time till touchdown brings me round again to find I'm not the man they think I am at home. Oh no, 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 I'm the man.
The reaction in these model rockets is shown by this balanced chemical equation. Citric acid and sodium bicarbonate react with water to produce carbon dioxide and sodium citrate. In this reaction, carbon dioxide is the gas that is evolved.
This CO2 generation produces an increase in pressure within the closed system of the film canister. The increase in pressure creates a force high enough to blow the canister off the lid, following Newton's third law of motion.
We noticed water is a reactant and a product, and therefore is probably a catalyst. The citric acid in Alka-seltzer is packaged in anhydrous form, and the packaging itself is a watertight container. Therefore, the reaction is thermodynamically favorable. While a quarter tablet was mostly reacted, a half tablet was the best performance because it was able to build up pressure more explosively. Using a small amount of nearly boiling water provided more initial energy, resulting in a higher launch, and allowed for more volume in which gas pressure could build. The use of hot water would have immediately added water vapor pressure to the system. Contrary to predictions, an uncrushed half tab was best, probably due to larger surface area and more nucleation sites. In addition, excess Alka-seltzer was present for the reaction, maximizing CO2 production. More Alka-seltzer was not necessarily better, probably because the canister cap releases at a certain pressure, so balance is the key. Crushed tabs, while faster, did not produce the same results. This may be due to stored energy in a full tab. Nucleation of a large piece could lead to higher energy gas bubbles.
In order to calculate the pressure that was contained within the canister, we first needed to find the initial velocity that the canister had when it left the ground. In order to do this, we used one of the equations we learned in physics, which was that the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the height traveled. For this, we assumed that the final velocity was 0, with that being at the peak of the rocket's travel. The initial velocity was what we were looking for. The acceleration was negative 9.8 meters per second squared, and the distance traveled was 10 meters or 33 feet. In addition to this, we used Bernoulli's law for fluids in order to find the total pressure within the vessel. For this, it is the kinetic energy divided by the volume of the container. For this, the pressure would end up being 1/2 m times the initial velocity squared divided by pi r squared h. For this, we used the max height as 10, and we got that the initial velocity was 14 meters per second. In addition to this, we used the mass without the cap of the container to be 0.004 kilograms or 4 grams, and the volume to be 7/8 of the total volume of the canister due to the 1/8 of water being used. This came out to 34.125 centimeters squared or 0.000034125 meters cubed. From this, we got that the final pressure was 11,487.2 pascals, and because we use Bernoulli's law in order to find the pressure of the vessel, we have to assume that this is a real gas, as it is acting like a fluid where the molecules are interacting with each other.
Possible modifications for the film canister is adding a nose cone and fins for increased aerodynamic performance and stability. Also, to increase the amount of pressure the canister is able to contain, A rubber O-ring could be incorporated into the design of the cap to create a tighter seal.
A rocket man.